we show the uniqueness of solution to the Laplace equation. Laplace equation is del squared v equal to 0, together with the boundary conditions. Let v1 and v2 be both solutions of the Laplace equation so that del squared v1 is 0 as well as del squared v2 is 0. These two statements imply that del squared v1 minus v2 equals 0. The solutions must also satisfy the boundary conditions. So v1 at the boundary must equal v2 at the boundary must equal vb, the given boundary condition. This implies that v1b minus v2b equals 0. Now we use the following identity from vector calculus. So the divergence of v into d, v being a scalar function, d being a vector valued function, equals the quantity on the right hand side. Now for using this identity in the proof, we choose the scalar to be v1 minus v2, where v1 and v2 are assumed to be the solutions of the Laplace equation, and d as the grad of v1 minus v2. Now with this choice, the identity takes the following shape. Now we integrate the identity over the whole volume enclosed by the surfaces in question, so that you have this statement with volume integral taken all the way through, both left hand side as well as right hand side. So the terms are labeled as shown. So if we apply the divergence theorem to term 1, applying the divergence theorem, we have that it evaluates to 0 because we have v1 and v2 is evaluated at the boundary, and we showed that v1b minus v2b is 0, so the right hand side is 0. So that term 1 is 0. Now term 2 is 0 by hypothesis because it has del squared v1 minus v2, which is 0. Now the remaining term, which is term 3, this term, must be 0 because term 2 and term 1 have both been shown to be equal to 0. So term 3 must be equal to 0. The integrand is strictly positive quantity, and the volume integral evaluates to 0. This could only happen when the grad, which is occurring inside the square term, must be 0. So this could happen when the v1 minus v2 is identically 0, or when v1 minus v2 is a constant. So this constant may now be evaluated by using the boundary condition. So applying the boundary condition to v1 minus v2, we have v1 minus v2 at the boundary is v1b minus v2b, which is shown to be 0 previously. So which implies that v1 equals v2. So the conclusion is that the solution to the Laplace equation is unique.